Okay, basically we finished talking about a vector space. We talk about vectors. In vector space, the members are vectors. So with the vectors, we can add them. Oh, no, hold on 1 second. I'm sorry. No, this is not 220. This is not a 220 class. This is 150. So what we're talking about, right? We're talking about limits. Basically, we finished talking about limits, right? Left limit, right limit. We talk about if a limit exists for a function at a point, then the left limit equals to the right limit. And then we talk about function values. If the limit exists and equals to the function value at the point, it means the function is continuous. So to find the limits of a function, we have a couple of tricks. Right? One trick is to simplify the function. And we have identity when the angle approaches 0, sine x, sine of the angle over the angle equals to 1. And sine x over x can be raised by any power in identity. And also finding limits, sometimes we use the difference of squares. We multiply by its conjugation to get rid of the square root. That's another trick. Okay, we did do this. Yeah, continuity means the limit of the function at a point exists and equals to the function value. So three things are the same: left limit, right limit, and the function value. Like this graph, at every point is one piece of string. So of course it's a continuous function at all those points. And at every point, the left limit and the right limit and the function value coincide. All right. Okay, so I left these three for you to do, right? Other than your homework. Let's start with those three. So 4, 12, 16. Okay, Victoria wants to show 4. Carlos wants to show 4 also. Noella wants to show 12. Julie wants to show 12 or 16. All right, great. Okay, let's go. We start with Victoria. Let me make you a presenter.
For number 4, the continuous intervals are open bracket -4, comma, -2, parentheses. Then it's parentheses, -2, 2, parentheses, and open bracket 2, 4, parentheses, 4, comma, 6, parentheses. Then it's parentheses 6, comma, 8, parentheses.
Okay, let me write here. So basically, we're trying to find the domain of this function. Just to say, the function is continuous at the point. It's the same thing to see the domain. Right, so you are saying bracket -4, right? Up to 2, open parentheses, then to -2, -2, -2 up to 2 open parentheses. You know, in between you can write a unit, but it's difficult for me to write units, so I just write them individually. Then from 2 with bracket, 2 up to 4, then 4 up to 6, then 6 up to 8. All right. Yeah, so these brackets and the close open parentheses are important notation. Bracket means the value is in the domain. Let's see the first one. -4 is in the domain of this piece. So -4 up to 2 with open parentheses because it's open circle. Then again, the next one is open circle, open circle. So open parentheses up to 2 open parentheses because it's open circle. But next one is bracket because this is a solid dot. 2 is in this domain. So 2 up to 4. Because this seems to shoot up to infinity. So 4 is not in the domain. So then from 4 up to 6. So from 4 up to 6, open, so open parentheses, also open parentheses, 6 up to 8. Okay, great. All right. Carlos, do you have, if you have different answers, you may show for 4. If you have the same answer.
No,
yeah.
I have the same answer.
Okay, all right, thank you.
Thank you.
Okay, Noella, 12.
Good morning, Professor.
Good morning.
So for this question, using the properties of limits, I decided to break down the function into components consisting of as x approaches to limit as x approaches to 3x to the 4th plus limit as x approaches to -5x plus limit x approaches to cube root of x squared plus 4. So
Right.
from there, we can simply plug in the given value of a, which is 2, and we get 40. So given the definition of continuity, f of a is defined, meaning f of 2 is defined, and the limit of f of x from both the right and the left side are equal to one another, meaning that continuity exists and this function is continuous.
Okay, yes. So we're trying to find the left limit. Left limit is f of a. Right limit is also f of a. Then f of a is a equals to 2. So f of 2. Yes. All right. Julie, you want to do 16?
Yes.
Okay, please.
So the function is discontinuous because at x equals -2, it has an infinite discontinuity, which just means that both one-sided limits are infinite, and then the right and left sides aren't equal. So the limit as x approaches -2 of 1 equals 1, and it is defined, but the limit of f of x as x approaches -2 equals the limit as x approaches -2 of 1 over x plus 2, which doesn't, which is infinite. And so f is continuous for that reason. And so I drew a graph, but I don't know if I could share that.
You want to show your graph?
Let me see if I can do that.
Maybe I can draw for you. Let's see. So let's see. So -2 we have here, right? But how do we draw this 1 over x plus 2? This is a transformation of 1 over x, but horizontal transformation. So remember 1 over x is the graph of this. We have this piece, we have this piece. And those two pieces are symmetric with the origin, right? But now 1 over x plus 2 means x is shifted to the left for 2 units. So that means the graph now is shifted. Let me draw another vertex. Let's see, this is a -2. The x value is -2 here. So think about as the y-axis is being moved from here, from the 0, 0 to -2, 0. So now we have, so now the graph, we have two pieces. We still have those two pieces. We still have those two pieces of graph like this. This goes to infinity, this goes to infinity, 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 right? So this is a -2. Well, if it's so 1 over x plus 2, if x not equals to -2, -2 here, we don't have the graph. So, but now x equals to -2, we forced the function to be 1. So that means here, so if x equals to -2, we see, let me make a point here. Oops. All right, let me choose one here. Oops. Right, so the function value of f of -2, we forced f of -2, we forced it to be 1 right here on the, so this is a -2 value, and this is a 1. Okay, so what's your proof? Your proof is saying this function is continuous or not continuous?
It's not continuous.
It's not continuous. The picture, is your picture same as this picture?
Yes.
Yeah, that's it, right? Because this point, the function value is right here. And the left limit of the function at -2 goes to -infinity. The right limit goes to positive infinity. But the function value is 1. Okay, great. Any questions? Anybody has any questions? Okay, if not, let me see. Let me find a couple more questions to do. So this is a continuity. Maybe I go to. Okay, let's try 35. So you all try 35, all right? Even 32. Something called squeeze theorem. Okay, both of these use squeeze theorem. Okay, then 36. Okay, try this 3. I'm going to check the attendance while you are trying. Okay, someone has question. Let's see. When can we begin to do the quizzes on? You can do any time, whenever you're ready, right? The 3 attempts. If you try 3 of them, I'll choose the best grade out of 3. If you do 2 of them, I'll choose best grade out of 2. But if you feel comfortable, you only have to do 1. And each one, I think you have a couple of tries. All right, for now, try 32, 35, 36. You know what? Okay. Yeah, okay, try this 3. I'm going to take attendance here. Okay, if someone's ready, all right. Amir wants to try 35. Anybody wants to try 32? Okay, Sophia 36. Anybody wants to try 32? Okay, let's go with 35 first.
Okay, so for 35,
Right.
so it says the limit as x approaches 0 of x to the 4 times cosine of 2 over x is equal to 0. So what I actually did was I actually used the trigonometric identity. So I used the half angle identity, cosine of x over 2 equals plus or minus square root of 1 plus cosine of x over 2. And I noticed that 2 over x is the reciprocal of x over 2. So you can rewrite this expression as 1 over the square root of 1 plus cosine of x over 2. From there, I substituted 0 in, and I got 1 over square root of 1 over plus or minus square root of 1 plus 1 over 2, and that was simplified to plus or minus 1. And then from there, all I would do is for the 2 over x, I would either substitute plus or minus 1, and then for the 0, x to the 4th, I substituted 0, and we have 0 times cosine of 2 and 0 times cosine of negative 2, which are both equal to 0.
Okay, great. The trick is to use the double angle formula, or half angle formula,
Yes, I
right?
used the half angle.
Right. You can use either one. Well, here I write double angle formula. So cosine 2 over x, we can write as a 2 sine, because we want to use identity. 2 sine 1 over x squared minus 1. But in any case, right? So the trick is this, to use this identity. Okay, anyone has any question about this, 35? All right, let's go to 36. Sophia, 36. Okay, Sophia typed in the chat. To remove the radical on the left side, okay, to remove the radical on the left side of the equation, square both sides. So 36. So we square, all right, if we square both sides of the equation because there are no values to the left of 0 in the domain of x raised by half. Okay, so in any case, so Sophia's saying proof. No, Sophia, you're saying 1 plus sine squared 2 pi over x. The limit does not exist. Raising 0 to any positive power yields to 0. Okay. I have trouble here. If part of it, the limit does not exist, then we cannot go further, right? We cannot go further. But 36, we can prove the limit equals 0. Let's see. So this basically will have two parts, right? We distribute square root of x inside. So we will have limit of x approaches 0 from right hand side, square root of x plus limit of x approaches 0 from right hand side, square root of x times sine squared 2 pi over x, right? The first part is just 0, because square root of x is polynomial-like. We can plug in 0. So the first part give us 0. All we have to deal with, just like Sophia is saying here, all we have to deal with is limit x approaches 0 from right, square root of x times sine squared 2 pi over x. So now we want to use identity. All we have to do is the factoring 2 pi over x squared. Let me use. Can I use sine square x equals to half of 1 minus cosine 2x? You know, maybe I could, but yeah, maybe I could, but that wouldn't help me to use the identity, right? Because I want to be able to use the identity. The identity is saying the limit when x approaches 0. So I left with the sine square of 2 pi over x. I have to deal with this. When, of course, when x approaches 0 from x approaches to 0 from right. Okay, let me just ignore this. So basically, all we have to deal with is this piece. Oh, square root of x, of course. Square root of x. What do we need? We need to multiply by 1, right? This 1 is 2 pi over x squared over 2 pi over x squared. Because we remember sine of the angle divided by the angle equals to 1 under the limit when x approaches 0. So we can use that. So we manufacture the square term of 2 pi over x. Then we simplify from there. So what do we get? So we multiply by that. Then we can analyze from there. Okay, because this is right limit. Remember, right limit and the left limit always exist. But the trick is to do this. Okay, Sophia, is that? Oh, you cannot speak. But anyway. All right. So anybody? Okay, let's go back to 32. 32 is saying use squeeze theorem. So a lot of times we use squeeze theorem. So what is squeeze theorem? Squeeze theorem is saying sine x. In this case, we know sine is bounded, right? Sine is bounded in between of -1 up to 1. So sine of any angle, well, in this case, is sine pi over x, right? Sine of any angle, the value be bounded in between 1 and -1. So then from the left-hand side, right-hand side, and also in the middle, everybody, so 3 terms here, we multiply square root of x cubed plus x squared. We multiply this term. So then that means this guy is bounded by square -1 times this term, turn this term to be negative, and 1 times this term. Right? Then now we can plug in 0 because because square root of x cubed plus x squared is polynomial-like. So 0 is in the domain. So we plug in 0. So we will have left-hand side equals 0, right-hand side equals 0, and the middle one is in between of 0 and 0. If it's in between 0 and 0, it has to be 0. That's a squeeze theorem. All right, any questions for this? Okay, already checked attendance. Let me see. If you came late, later on, let me know. If I haven't found out you're late, because I marked absent for today. Yes. Okay, let's try. So the question is, can we use squeeze theorem for 35 and 36? For 35, yes, you could use what do you call it? The double angle formula, right? Once you use the double angle formula, you see sine appears. So you want to manufacture sine. Sine appear, then x raised by 4 times these two terms. Well, x raised by 4 or negative x raised by 4 is a polynomial. We can plug in 0. So all we have to deal with is the cosine term, the sine term, right? Yes, you can try that too for both of them. You can try to use the squeeze theorem. Okay, any other questions? All right, okay, good. Right, if you're late, let me know. I'll mark you for your attendance. All right, so anybody has any questions from your online homework or anything for the material? Okay, if not, we're going to how to prove 36 use the squeeze theorem. I lost myself. Where was it? It's similar to the one I showed you right here. Squeeze theorem is basically you want to manufacture. Let's see this case, 36, right? You want to manufacture. Let's just take the middle part. Take the middle part. We don't really have to take the middle part. Take the because this is sine square. Sine square like Amir advised in beginning, we could use half angle formula to change this. Remember, 2 sine square minus 1 equals the cosine to double angle. Because if we have a square term, that we won't be able to manufacture -1. It's bounded between -1 and 1. Or sine square, 2 sine square, 2 sine square minus 1. So we have to manufacture that. So we have to multiply by half, multiply by 2 inside, then minus 1 here, then that means plus 2. So once we have 2 sine square minus 1, that changes to be cosine 4 pi over x. Cosine 4 pi over x. You know what? 36 is not a good idea to use squeeze theorem because we have a square term here. What you can do is, let me see, because it's difficult to change the whole thing to be square root and square. You know, you can use it, but it's a lot of things involved. Yeah. 36 may not be a good idea because we have a square term. Okay. Then you have to change things around. Try not to use square term for squeeze theorem for this. So Kang saying he raised the limit to the power of e, then use squeeze theorem. Limit the power, you raise the limit to the power of e. What do you mean? What do you mean raise the power to the power of e? Because what I say is difficult to, if we could change, okay, the first part is easy, right? Square root of x equals 0. Limit of this equals 0. But the limit of square root of x times this one, oh, we still can, all right? Because we're only left with this. Then we can think about the whole term being raised by square. So write, limit of square root of x, then limit of sine squared 2 pi over x. If you want to force yourself to prove by limit by squeeze theorem, you just show this part. The limit when I approach 0 from the right, sine square of this term, right? Then what do? You raise the whole limit by square. You say limit of sine 2 pi over x square. You raise the whole thing by square. Then you prove the limit of sine 2 pi over x is in between of -1 and 1. Right? Then when you multiply square root of x, in this case it will be fourth root of x because you raise the square. Then you prove the square root of x times sine square 2 pi over x. You rewrite it as a fourth root of x sine 2 pi over x, the whole thing raised by square. Then you prove the inside fourth root of x sine 2 pi over x is in between of negative square root of x and square root of x. And when you plug into 0, of course, negative square root of x is 0, and square root of 0 is 0. So that's why this 2 is in the middle of 0. It has to be 0. When you raise 0 to a square term, you still get 0. Okay, that's one way to prove it. All right, any other questions? All right. When is the midterm of first major test for term or everything will be unknown? When is the midterm? You mean the exam? We don't have midterm. We don't have midterm, right? We said it's just only one final. Any other questions? Okay, so today we're going to talk about limits involve infinity sign. Let's see. So let's see those examples. So the limit x approaches 0, 1 over x squared, we have this graph. And at 0, the limit does not exist. But in another case, we can write the limit of x approaches 0, 1 over x squared equals to infinity, right? See, the left limit goes to infinity. The right limit also goes to infinity. So we can write the limit of this equals to infinity. Of course, infinity is an idea. It's not a number. So that's why sometimes we equal those two notations. You see, if the limit goes to infinity, we also can see it does not exist because it's not a number. Remember the definition of limit in the very beginning? We're saying if the limit exists, it's a finite number. It's not infinity. So that's why we equal those two ideas. So let's see this definition. The notation limit of x approaches a of x equals to infinity means that the value of f of x can be made arbitrarily large by taking x sufficiently close to a. Right, so that's all. Just like the picture shows, just like this picture shows. The left limit goes to infinity, the right limit goes to infinity. So we're seeing the limit at this value, approach to this value is infinity. Similarly for negative infinity. Right, like this function, if we put a negative sign, that goes to negative infinity. Because both of the values will be down. Let's see if we have this graph. We don't really have this graph. But this graph just put this branch on the third quadrant, put this branch on the fourth quadrant. So it goes to negative infinity because we negate the y value. So the line x equals to a is called a vertical asymptote. We know this before, right? If the value is not in the domain, it creates a vertical asymptote. So limit of x approaches a of the function equal to infinity means the left limit goes to infinity, the right limit also goes to infinity. Similarly for going to negative infinity. Let's see these two examples. Find the limit of x approaches 3 from the right of 2x over x minus 3. And also the left limit. So find the left limit and the right limit when x approaches 3 of this function, this rational function. And of course, 3 is not in the domain of this function, right? But we can draw the graph. So how do we draw the graph? Well, this book has it. Let's just follow this. So any rational functions, right? We think about the basic function 1 over x. So the graph looks like this. So from the right, we see, so the y-axis, because see the denominator is shifting to the right 3 units, right? So basically the y-axis is being shifted 3 units to the right. So now this 3, 0 is the point of symmetry for those two branches. So the left limit goes to negative infinity, the right limit goes to positive infinity. All right, and that's it. And it's difficult to well, actually we could there's something called ignore rule. We use well, let's talk about that later when it comes along. Let's see example 2. Any questions for example 1? Left limit and right limit always exist, all right? So the limit, of course, the limit of x approaches 3 for this function does not exist. Let's see example 2. Find the vertical asymptotes of f of x equals to tangent x. So basically find all those values not in the domain of this function. By our pre-calculus knowledge, we know tangent function is this way, right? It discontinues at every k pi over 2. k is an odd number. So k negative 1, negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, so on and so forth. All the odd pi divided by 2. And let's think about at pi over 2, right? Choose at pi over 2. The left limit goes to positive infinity. The right limit goes to negative infinity. All right, so this happens at every odd pi divided by 2. So what do we write? We can write as x value equals to 2n plus 1 pi divided by 2. When we write this way, then n goes from 0. Then n can be any integer. Okay, think about n is 0. Then we get a pi over 2. Think about n is negative 1. We get a negative pi over 2. So on and so forth. Right? So n is an integer. So x, basically this is saying x, the function discontinues at every odd pi. So when we want to represent the odd, we write 2n plus 1 or 2k plus 1. So this forces this term to be an odd number divided by 2. Okay, limit at infinity. So now the above is saying limit equals to infinity. What about the limit at infinity? Let's see this example. This example is x squared minus 1 divided by x squared plus 1. Limit of x approaches infinity. So when x approaches infinity, something called ignore rule. So this is another tool we can use for finding limits. Ignore rule. Okay, what does it mean ignore? What to ignore? Ignore sorry, I'm missing E here. Ignore the lower terms for numerator and denominator. Okay, so this is for limit approaches infinity or negative infinity. Okay, so when the x value approaches infinity or negative infinity, we use ignore rule. Right. So when x approaches infinity or negative infinity, we apply ignore rule. Ignore rule is saying just take the leading term of the numerator. Ignore the lower terms. So the leading term in the numerator is x squared. And similarly, take the leading terms of the denominator. Ignore the lower terms. So the leading term is x squared also in the denominator. So then this becomes limit. So limit just x squared over x squared. Of course, something divided by itself is just 1. So limit of 1 is 1. All right, so when x approaches infinity and negative infinity, basically this is a tool to find the range. So this is one way to find the range of the function. So when we give us a function, when we want to find the range, so the domain means the x value, the range means the y value, right? So when we want to find the range of a function, we could do this. We could take a limit, then let x approaches negative infinity and x approaches infinity. So this is telling us the range, right? The range. So this function will never be 1, approaches to 1, like this graph. So this is a graph of the function. You see, because the limit of this function value is 1, that means it creates horizontal asymptotes. That means the value approaches to 1, the function value approaches 1, but will never be 1. All right, so that's the range. So limit of x approaches infinity. So we call ignore rule, okay? Whenever we see x approaching infinity, we use ignore rule. Let's see some more examples. All right, let's see this one. Example 4. So find the limit of x approaching infinity 1 over x. Right? Let's think to use ignore rule for this. Well, the leading term for numerator is just 1. The leading term for denominator is just x. 1 over x, right? Think about infinity. So think about it, you have one apple shared by all the people in the world. So how much apple each one can get? Almost none, right? You can argue, you can cut the apple into tiny small pieces. Then maybe everyone gets a little piece. But the idea is infinity. Infinity is, as big as you can think, the number. So 1 over infinity is 0. So 1 over infinity is 0. Negative infinity is the same thing, also 0. So let me put it here. Infinity equals to 0, okay? Can I say equal to 0? Just approach to 0, okay? So whenever we say 1 over infinity or 1 over negative infinity, that's 0. Well, also we can see from this graph, right? The left limit goes to negative infinity at 0. The right limit goes to positive infinity at 0. Okay, so that's this one. Let's see some more examples. Let's see this one. Okay, example 5. So we want to evaluate this rational function when x approaches infinity. So what do? We use ignore rule. Take the leading terms. Forget about the lower terms. Forget about negative x. Forget about negative 2. Forget about 4x. Forget about 1. So left with 3x squared over 5x squared. X squared over x squared, that's 1. So left with 3 over 5. So limit of number, just a number. So the limit is 3 over 5. Right? So that's a simplified version of this example. But why we can use ignore rule is because of this. Because we can divide it by the higher terms. So the higher terms in the numerator is x squared. The higher term in the denominator is x squared. So let's divide it by 1 over 1. So we divide the numerator by x squared, we divide the denominator by x squared. Once we divide, we get this. Numerator becomes 3 minus 1 over x minus 2 over x squared. Similarly for the denominator. Remember we said 1 over infinity becomes 0. Of course 2 over infinity squared becomes 0. So all those terms disappear, they become 0. They become 0, so we're left with 3 over 5. All right. But the process is in this. But for us, just remember ignore rule. Okay, I have a question here. The question is saying, what if the numerator and the denominator's highest power are not the same? That's good. That's good. Let's think about one example. Let's think about maybe the rational function is x minus 1 over x squared plus 1. Let's use this example, right? We could use ignore rule. Then after we ignore the lower terms, we have x over x squared, right? Then when this can be simplified as 1 over x. Then when x approaches infinity, 1 over infinity, that's 0, right? Well, let's use another. Let's do another example. What if we have x cubed plus x minus 1 divided by the denominator, maybe x plus 1. Right. In this case, let's ignore the lower terms. When we ignore, we have x cubed divided by x. Well, what is that? That's just x squared. Well, when x approaches 0, what does x squared approach to? Of course, 0, right? Okay. Any other questions? Okay, I give 2 examples, right? One example is the numerator, the degree of numerator is lower than the denominator. In this case, we get 0. You know, when x approaches 0, when x approaches infinity, we get 0. Oh, this is infinity. In another case, is the numerator, the degree of the numerator is higher than the denominator. In that case, which is when x approaches infinity, that's just infinity, right? In this case, just infinity. When the degree of numerator is higher than the denominator, it goes to infinity. When the degree of numerator is lower than the denominator, it goes to 0. Okay, let's see this one. So this one is polynomial-like. If it's polynomial-like, let's see. So we have 2 parts. We have square root of x squared plus 1 minus x. So what do we do? So let's see. Let's multiply by its conjugation because it's difficult, right? Because when we take the limit of this part, we get infinity. And minus limit of this part, we get infinity. Nobody knows about infinity, subtract infinity, right? So we don't know infinity, subtract infinity. So what do we do? So let's multiply by its conjugation. This is always a trick to get rid of this square root. Multiply by its conjugation, simplify, so we get this 1 over this. Now we can apply ignore rule. Once we get this part, we can apply ignore rule. Ignore the lower terms, take the leading term. So the leading terms of this denominator, from this part we get x. From this part we get x. So get a 1 over 2x. Right? Then 1 over infinity, that goes to 0. That's how we prove this is a 0. As you can see, this is just, requires algebra skills, right? It's like, we go one way, it's a dead end. So we manufacture another route, multiply by its conjugation. Okay. Any questions? Okay, let's see this one. Example 7, limit when x approaches infinity, sine 1 over x. We don't get a rational function. So this is a trig function. So how do we do with a trig function? So ignore rule is for rational function. Because the numerator is polynomial, denominator is polynomial. So we can use ignore rule. But for trig function, we may not use that. So what do we do? Let's simplify, right? Let's call 1 over x another variable t. Then think about t approaches 0 from right, and t, because, okay, 1 over x, let t be 1 over x. Right? If x approaches infinity, it's the same to say t approaches to 0. So that's a trick. That's a trick. So we substitute with a temporary variable. So to approve this is the same to approve limit of t approaches 0 sine t. Right? So we rewrite this as a limit approaches t from 0 to the right hand side, sine t equals to 0 because x approaches positive infinity. And we know that sine 0 is 0 because we can plug in this, right? 0 is in the domain of sine function, so that equals 0. So the trick is to change the variable. All right. So in mathematics, a lot of times we change the variable. And later on, right, are we going to do that? Right. So in integration, we're going to change the variable called U substitution. So okay, so those are examples of limit equals to infinity or limit at infinity. Okay, any questions? Right, I see some exercise maybe. Oh, okay. This is another example we need to know, a trick. Let me see this one. Oh, okay. So this is the infinity limits at infinity. So limit of function x approaching infinity equals to infinity. So I have two infinity signs here. For any polynomial, this is true. Let's see, limit of x cubed when x approaches infinity, right? That would be infinity. Same thing for negative infinity. X approaches negative infinity, x cubed, that will go to negative infinity. So I have these two kinds of notations, like the graph shows, right? X value goes to negative infinity, the function value goes down to negative infinity. X value goes to positive infinity, the function value goes up, positive infinity. Let's see this one. This one is saying the function is x squared minus x when x approaches infinity. So split into two parts. Then we get infinity minus infinity. So nobody knows about infinity minus infinity. So the limit law cannot be applied to infinite limits because infinity is not a number, but a concept. So what do we do? So we can write it like this. Limit of x approaching infinity, we can factor out. We factor out x times x minus 1. Then we can split. So split limit of x. When x goes to infinity, that's infinity. And also infinity minus 1 is also infinity. Infinity times infinity is infinity, right? Because it can only be bigger. But for minus, we have no idea. Let's see this example. This example, we can use ignore rule, right? We take the leading term of the numerator, we take the leading term of the denominator, so we get x squared divided by negative x. That's negative x, right? So negative x, when x approaches infinity, negative x will approach to negative infinity. So this one we can use ignore rule. Let's see these precise definitions. So f is a function defined on some open interval and contains the number a. So a is in the domain, except the possibility at the a itself, or a may not be in the domain, open parentheses. Then limit f of x approaches a, f of x equals to infinity. Like, okay, it's not a is not in the domain. It creates vertical asymptotes like this. So we'll see. Okay, we're not going to this delta epsilon ideas. All right, let's choose some examples, some practice. Okay, let's try the 17. Yeah, we have time. Let's try 15. So, you know what? 15 might be a homework. Let's try. Those are too easy. Let's try cotangent. 20, 24, 28, 32. Okay, let's try these 5 questions. Okay, I'm gonna call, so I check the attendance. We have 28 showed up today. Let me just make sure. Yeah, if you want to do some numbers, write down the number in the chat. Just want to make sure those students are not here. I didn't want to mark you wrong. So this is Zara. If you're here, let me know. Zara, first names ABOUALHASSAN. Then Michael, Angeles, ANGELES, MAIKEL. This is Ashmawi. Last name ASHMAWY. Castillo, last name CASTILLO. Katie, last name HERAS. Raymond Lin. Karishma, last name Pandy, PANDAY. Anna, last name PIRTSKHALAI, Anastasia, last name SKRIPCHENKO. This is Mokera, last name SULTONOVA. Fedwa Osama, last name YOUSEF. All right, so those people are not in today. Okay, let's go back to see. Okay, so Malika wants to show 20. Raphael show 16. Andrew show 24. Yeah, Julia, you're here, right? If your name, I did not mention your name, that means you are here. Okay, count to 32. All right, so let's start with Malika, 20.
Hello. So for 20, you look at the first term. So like for 1 minus x to the power of 2, you would look at x to the power 2. And then for the denominator, you would look at x to the power of 3. Since the numerator has the lower power, it's going to be 0 since it has a lower degree than the denominator.
Okay, but you have to show the right term. Okay, so this is not the numerator, the highest term is not x squared, but negative x squared, right?
So you
You
wouldn't
see
look at the powers, you would look at like the actual first term.
the whole term, not the first term, the leading term. So let me ask you this question. What is the leading term for numerator?
So it's going to be the first one, so 1.
No, the leading term. The leading term means the variable has the highest power.
So it would be negative x to the power of 2.
That's right. So you take a
Yeah,
negative x squared, not x squared only.
Oh, so you look at also the
The
negative.
sign is
Yeah,
important, right? The
okay.
sign is part of it. Negative
Okay.
x squared. Okay, that's 20. The next one, 16. Raphael.
Hey, good morning.
Good morning.
So we know that cotangent x is equivalent to 1 over tan x. And we also know that, for every pi or, even number, pi over even number, or the same number, you get an asymptote, unfortunately. So this obviously makes our job a lot harder, but we do know that as we approach from the left in general, the y value would be negative infinity as we approach that asymptote from the left. So we know that 1 over tangent x would actually go to negative infinity if we approach pi from the left.
Hold on 1 second. So you are using the graph of tangent, right?
Yes.
But here, cotangent is 1 over tangent. Right? It's 1 over tangent. So we may not use the graph of tangent, but we have to think about the graph of 1 over tangent if you want to go that way. But what is another way of thinking about this? Cotangent, remember tangent equals sine over cosine, right? So cotangent equals to cosine over sine. Does it make sense?
Yes, yes.
Yeah. Maybe we can use this. Because we don't have pi over 2. We don't have add pi over 2 here. You see the point? The point is pi. The point is pi. And the pi is in the domain of tangent. So let's, hold on a second. Right, this may not help. Yeah, forget about this. Forget about this. Yeah, I think, right. I think you're right. Okay, let's go to the, okay. Okay. So Raphael, can you repeat your steps?
Sure.
So have this pi here. Right.
So as I mean, I'm probably wrong, but I know that cotangent is equivalent to 1 over tangent x, right? And we know that
Right.
there's an
So let's flip
asymptote.
this.
Yeah.
So you can think we have a new, so other graph is being flipped. So 1 over, so we have this, what do we call it? 1 over x, x equals to y. So what's it, so.
Oh yeah, I probably messed up my graph, but yeah.
But it's okay, we're all trying here. I'm trying also. I don't have the answer ready in my head also either.
Yeah. I mean, I'm looking at a graph of tangent x right now, and
Okay.
there is pi comma 0 on it. So I do suppose that it would be but it would be 1 over 0 technically. So then you have to do trig identities.
Okay. All right, let's see someone else is saying something here. Yeah. Andrew is saying we reflect or flip the graph of tangent. Right, that's what I was trying to do. So we make graph from there, then just get, yes, right, reflect over y equals the axis. Yeah, then we get 1 over 1 over tangent. 1 over tangent graph. 1 over tangent graph we see at pi equals 0. Yeah, this one is better to do, probably to do with the graph. All right, thank you, Raphael. Every question we have different ways to do it, and I should remember my numbers. The number of the page. Okay, here. All right. Oh, okay. Victor thinks he's right. He was right. He was right about. Victor, what were you thinking about? You were thinking about Raphael is right.
Yeah, that's just what I inferred looking at the graph of that.
Okay, you want to back him up? Okay, go ahead.
Just because looking at the graph of 10 of x, which I don't have pulled up anymore, but I think that um, when the graph approached the left side, it was approaching.
I cannot hear you.
So I don't know.
Okay.
I might have audio problems then.
Oh, okay, I can hear you now.
Oh, I was just saying that when I was looking at the graph, I saw that when the graph approached pi from the left side for tan of x, I think it was approaching positive infinity. So I inferred that then the opposite graph might be approaching negative infinity, and then I looked up the graph of cotangent, and that's what I got as well.
Yeah, what is the graph of cotangent? Cotangent is 1 over tangent, right?
Yes.
Right. So tangent pi equals 0. So we may not look at the graph of tangent itself. If we have a cotangent graph, we can look at the cotangent graph to get the answer of x approaches pi from the left. If we look at the tangent graph, we have to think about its inverse, one because it's 1 over tangent. We could reflect over y equals x line to think about that too. Approach to the left. Yeah, I don't have a cotangent graph here, but let me do this. Let me show you guys the cotangent graph. So I use decimals to graph. So f of x equals to cotangent x. Let me share this with you. Go here, stop sharing this. Decimals right here. Okay, so this is a cotangent graph. But unfortunately, they don't show us pi. They show us this is pi over 2, so pi, but we don't get to see pi. So this is pi over 2, this is 3 pi over 2. So pi is right in the middle somewhere here, right? If we have this graph in our minds, so we can see, you see this is 1 over tangent. Tangent goes this way. Tangent goes this way. Could just flip it. Right? For tangent goes to positive infinity, and then the cotangent goes to negative infinity, because it's 1 over tangent. All right, let's go back. Okay, so that's 16. Now, who wants to show 24? Yeah, it's negative infinity. You see from the graph. Okay, so anybody wants to show 24? Oh, okay. Angel, right?
Yes.
Okay, 24, then we have 28, 32 to go.
So I started by simplifying the denominator. So it's going to be x squared over x squared plus 1 raised to 1/2, since we use the ignore rule to get rid of 1 raised to 1/2, and then we divide x squared over x squared, which is equals to 1. So
hold on one second. What's your first step? Your first step, you're getting x squared over.
I simplify the denominator.
How do you simplify the denominator?
So I do x raised to 4 over 2 plus 1 raised to 1/2. And then I ignored 1 raised to 1/2. And then divided x squared over x squared equals 1.
Okay, so basically, let me understand you. So you're saying, taking the ignore rule, right? Just ignore this plus 1. Ignore the lower terms. So we have square root of x raised by 4. That's just x squared. Okay, so x squared over x squared is 1. Yes.
Yeah.
Yeah, perfect.
Thank you.
You're welcome. All right, 24. Then someone want to show, leave. So 24, what about 28, 32? We're left with 28, 32. Anyone wants to show 28? Not yet. Okay, Kang can show 32. Yeah, go ahead. Okay, so he typed in here, he said 32, you can factor out x squared, right? You can factor out x squared minus x raised by 4 by x squared times 1 minus x squared. As x approaches infinity, then x squared approaches infinity, 1 minus the negative x squared approaches negative infinity. So we have infinity times negative infinity. So that's just infinity times negative infinity, which is negative infinity. Okay, yes, great. That's it, right? So this is one trick, right? When we deal with this infinity minus infinity, we have no idea what that is, but we can factor out the common factors. Once we have infinity times infinity or infinity times negative infinity, and we can make a conclusion over there. All right, great. What about 28? Anybody try 28? 28, let me give you a hint. Use substitution, right? Because x approaches infinity, think about 1 over x. That means 1 over x approaches 0. Right? So let me type in here. So think about t equals to 1 over x. So to find out the limit of this is the same as find out the limit of you just change the value 1 over x. All right. Then you use the identity. When will the limits not exist for infinity? Remember in the very beginning we talked about when the limit reaches infinity itself. Before this section, we call it does not exist. So we can equal those two ideas. When the limit approaches infinity, it means the limit does not exist. Remember the definition of the limit? If limit exists, limit is a finite number. All right, so the two ideas at this section will coincide. All right. For 28, we can use squeeze theorem. For 28, we can use squeeze theorem. Okay, let's see, we have 0 divided by x squared sine square x divided by x squared. Oh, okay, he's saying Sine square is bounded by 0 and 1. Then we can divide by x squared for every place, because x squared is non-negative. Then but the problem is this. The problem is, what if x squared is 0? We cannot divide by 0. That's the only problem. Do you see that? We can always multiply by something, right? But sometimes we may not be able to divide by a thing, especially when the thing is a 0. So let's see. So we divide by x squared, say 0 divided by anything will be 0. 1 divided by anything, 1 divided this thing, because x goes to infinity, also be 0. So that's why this is squeezed in between zeros, also goes to 0. Yeah, I would buy this. This is okay. But because we talk about, substitution, so we can think as t equals 1 over x. So I encourage you to think this way also, all right? Okay, let's see now. Any questions? Okay, so basically we have finished the concepts of limit. So we're going to, at this point, I would encourage you to try the quiz in Norman, because we finished everything. I think you have a number of tries. And also you have the 3 quizzes for each, 3 or 4? 3 quizzes for each chapter. So if one is not ideal, you can try another one. I'll pick the highest score. So I'm going to talk about a little bit about derivatives, differentiation. We said in the very beginning of this class, we're going to cover 3 concepts for this course. The first concept is the limits, right? So when the value is not in the domain, we use the idea of limit. We consider left limit, right limit. If they agree with each other, if they do, we see the limit exists. But if the limit exists, the limit is a finite number. Then also we talk about if the limit exists and also equals to the function value, then we say the function is continuous at the point. And we have a couple of ways to approach limits. Right? One is the identity of limit of x approaches 0 sine x over x equals 1. Very useful. And sometimes we simplify the rational expressions. If the function is a rational function, we simplify by factoring or by multiply its conjugation to find its limits. Or sometimes if the limit approaches infinity or negative infinity, we use the ignore rule for rational functions. So on and so forth. That's for limits. So basically we have finished that. And the next one chapter is talking about derivatives, so differentiation. So what is the idea of that? Going back to linear function, we have a slope, right? What's the slope? The slope is the rate of change. It's how x change affects the changing of y. So it's a rate of change, right? How is one variable change affects the other variable changing. So this idea can be extended to different functions. Imagine for a polynomial function, right? We have these curves, we have these wiggles, and we can talk about the rate of change at a point. Right? For life, right? We use this for life all the time, right? The rate of change. We can talk about, if it's nonlinear function, we can talk about rate of change at a certain point. And we will see that, and gradually we give a name, we call differentiation or derivatives. Okay, at the certain point, what is the changing of one variable in terms of the other variable? So this is all about, derivative is all about rate of change, right? Of course, in life, we want to maximize profits, maximize our speed of doing things. We want to minimize our cost. We want to minimize, maybe timing to finish something, right? So we use this idea all the time, the differentiation. And firstly, we're going to get the definition of differentiation or derivatives from the idea of limits, right? Remember, we talked about difference of quotient. Difference of quotient right here. Remember, we have done something about this. F of a plus h minus f of a divided by h. Right? This is called the difference of quotient. H, consider h is a very small number. So this is saying, from one point to another point, what's the slope of those 2 points? Right? The bottom one, so h with h. Where does h come from? H equals to a plus h minus a. Think about this. We have 2 points here, actually. We have 1 point, a, and f of a. Okay, we have another point, a plus h, f of a plus h. The 2 points in this formula. 1 point is a, it disappeared in the denominator because h is a plus h minus a. We have 1 point a, f of a. Another point is a plus h, f of a plus h. So 2 points, right here. So a, f of a plus h, f of a plus h. So with these 2 points, we can connect those 2 points. So that's a line. Then we can talk about the rate of change or the slope of this line. The slope of this line, right? So this is called the difference of quotient. Difference of quotient is the slope of the line passing these 2 points. So then we'll define the derivative. We'll define the rate of change at that point is exactly the difference of quotient when the x value approaches a, or when the h approaches 0. So this is marvelous, because finding the rate of change or finding the slope of 2 points, we can always do, right? We know the slope equals the rise over run. We find the difference of y value divided by the difference of x value. But what marvelous about the calculus is this. This is only 1 point. You see, when h approaches 0, this is 1 point. So with calculus, so this is saying, give me 1 point, and I will be able to find the rate of change of those 2 variables at this point. So this is a phenomenon for calculus. Right? So from algebra, from 2 points, we can talk about rate of change. Now for calculus, use the limit idea, we can find the rate of change at 1 point. We don't need 2 points anymore. With the limit idea, it's just 1 point. So this is marvelous. All right, so this is studying. So why it's important to learn the limits first, but gradually, we see we don't really need to go through the definitions. So basically, this M here, we're going to make a definition of a derivative. We call this derivative of f at a. All right, so this is a little introduction for differentiation. All right, and if you could, and some of you are pretty advanced, so you may read ahead of me by finding questions. Yeah, okay, any questions? So far, if you haven't, present anything yet, make sure you try to do that, because when you present, you don't have to be right. All right, you don't have to be right. You don't have to be accurate. But it helps me to know how can I better help. All right, should I go faster or should I go slower? Will help me to better in teaching this course. All right. What is maximum times we have? You don't have maximum. I don't give you cap maximum times. Right. Whenever, but gradually I'm going to do this. Gradually I'm going to call on people, because for some people haven't shown any work yet. So at least, okay, let's say at least maybe like 15, 20 times, I would say. All right. But for some people, so gradually maybe I'll call on people, not to embarrass anybody, but to really know, how you are doing in this class. All right. Okay. Oh, I didn't leave you anything, right? So I'm not going to leave you anything for this week. So please focus on homework and your quiz. Right. So please focus on your homework and quiz. For the final, yeah, I think probably we will have a final, because the department requires a final. When is that? Final is the last day. I think it's December 12th. I will let you know. Final might be December 12th. Right? Okay, any other questions? All right, if not, I see you Monday. All right, so have a good weekend. All right. Thank you.